Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture number 61, and as I informed you in the last class, today is going to be tutorial 15 also. Okay, so the next two lectures are going to be two tutorial sessions. All right, so we'll embark on a tutorial. The first question for today is going to be that, remember that when we were discussing about rotational spectroscopy, I told you that the moment of inertia, the concept of moment of inertia pans out differently for polyatomic molecules than it does for the diatomics, and of course linear diatomics. I mean diatomics are always linear. Sorry, diatomics and linear polyatomic molecules. Okay, right? So in this tutorial, we shall in the form of question and answers look at that particular concept. Okay. So the question is going to be, what are the different types of rigid rotars in microwave spectroscopy and explain their significance in astrochemistry. So this is a question that we're going to address today to begin with. Okay, so the answer is, broadly speaking, now recall that while we were studying pure rotational motion, we had to assume that the molecule was a rigid rotor. In other words, it did not undergo any deformation as it was rotating about some axis. Okay. Now, in the lectures themselves, we discussed the case of only a diatomic molecule and the easier case of a linear molecule. Okay. Now, with polyatomic molecules, more complexity is added. Okay, so we shall address that complexity right here. The different types of rigid rotars are going to be A, linear and diatomic molecules. So they are characterized by only one I value. Right, we already saw this in the lecture, so I won't be spending much time on this, right? So, and the energy is given by Bj times J plus 1, where J is the rotational quantum number and B is the rotational constant. You can, of course, J is going to be 0, 1, 2, blah, 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 all right? So this is something we already discussed in the lecture, so I'm not going to reiterate about this yet again. There are other types of rigid rotars which are going to be much more interesting. And of course, if you want examples for these, CO, HCl, CN, etc. And all of these molecules are astrochemically relevant. Okay. Now let us look at some other types of rigid rotars. The other types of rigid rotar are what are going to be, call this like molecules containing spherical or cubic symmetry. Now, what would be some prominent examples? An example would be methane, right? You can also think of some molecule. I mean, this molecule might not have been discovered in the ISM, but it is relevant on Earth very much. Say P4, for example, right? Tetrahedral molecules, methane, P4. For example, some other example could also be something like CCl4, etc. Okay, you can also think of octahedral, very symmetric octahedral complexes, which can also be thought of as being molecules containing spherical symmetry. Okay, right? So, what is the connection with astrochemistry and microwave spectroscopy? Now, for these molecules, right? Now, for the spherically symmetric molecules, my Ix is equal to Iy is equal to Iz, right? And within the rigid rotor model, and note, and within the rigid rotor model, your dipole moment is also going to be 0. In other words, these are all non-polar molecules. So you would expect that within the rigid rotor model, you shall not be getting their microwave spectrum. Okay, right? So this implies that you shall not be getting their microwave spectrum. So please note this point. Okay. Now, it's very easy to imagine. Like you take, for example, methane. Methane is understood as having carbon at the center of a tetrahedron, right? If you assume all carbon and hydrogens to be point masses, your carbon is going to be at the center of a tetrahedron, and the 4 hydrogens are going to be at the 4 corners of a tetrahedron. All right. Now, the principal axis, right? The principal axis has to pass to the center of mass, which coincides with the carbon atom, right? So then, no matter like what axis you're talking about, right? The formula for moment of inertia, I equals sigma over I mi ri square, right? It's going to be the same for all the directions. That's an intuitive way to understand why they're all same. Okay, right? So the symmetry of the molecule tells us that the moments of inertia are going to be the same. But it is not just that. Beyond this, right? Because it's completely symmetric, it's also non-polar. And please recollect from a much earlier class, we're talking about somewhere around lecture in the vicinity of lecture 20 or 25 or something like that. I had told you that for a molecule to exhibit pure rotational spectrum, right? That is pure rotational or like pure microwave spectrum, right? The dipole moment should not be 0. In other words, the molecule should be non-polar. Okay, right? So therefore, these molecules which are non-polar, because the dipole moment is 0 due to perfect symmetry, and also the moments of inertia are the same along all the directions, right? They shall not be exhibiting microwave spectra at all. However, there is a catch. It is that it's only under the assumption of the rigid rotor model. In reality, for example, in methane, there could be some minor deviations from the rigid rotor model, and for some of these molecules, you could get the microwave spectrum due to the distortion from the rigid rotor model, which is actually called as the centrifugal distortion. Remember, we had this expression, right? The energy is given by Bj times J plus 1. This is under the rigid rotor model, but there was a minus, something like J times J plus 1 the whole square, right? Times the centrifugal constant, D or something, right? We had that expression, correct? So even though, like this term might be 0, the other term, due to the distortion from the rigid rotor model, right, can result in some sort of a microwave spectrum. Okay, right? I will just note this point over here. This is going to be page 5. However, so what I was telling was, however, distortion from the rigid rotor model implies you could get weak microwave spectrum. For example, for methane. For example, okay, right? So what is the implication for astrochemistry? The implication for astrochemistry is that molecules such as methane are best, right? Because the microwave spectrum is going to be rather weak, right? These molecules are best detected in space through vibrational spectroscopy. So the astrochemical, I've written astrochemical implication is that best detected in space via vibrational so what I've written is best detected in space via vibrational spectroscopy, because the microwave spectrum is going to be rather weak, right? Because anything that is going to be happening is only due to a deviation from the rigid rotor, and that for many of the symmetric molecule is not going to amount to much, right? So the symmetric molecule, right? It is really optimal to detect them via vibrational and of course electronic spectroscopy also, okay, right? Rather than rely on microwave spectrum, which is the most dominant method of detecting molecules in space, all right? So that's the aspect about molecules containing spherical or cubic symmetry, okay? Now, and we'll discuss about the next class of molecules. So the next class of molecules are what are called as, you can call them, this is C. The next class of molecules are what are called as like symmetric. You can call them symmetric molecules. The spectroscopists, they use the phrase called as a symmetric top, okay, right? So these are symmetric molecules which contain some kind of a partial symmetry, okay? I will explain to you. Now, consider for example, okay, right? Example, you take a molecule such as benzene. Let's say, benzene is this. Each of these corners of a regular hexagon represents a carbon atom, right? Now, of the three possible moments of inertia, right? Ix, Iy, and Iz. Now, if you assume these as point masses again, right? Benzene is a planar molecule, okay, right? So this is the benzene is planar. I mean, I'm talking about the ground state of benzene, okay? The ground electronic state of benzene is a planar molecule, right? And if you assume as all these is point masses, there are going to be two axes, right? Two axes passing through the plane of the board, right? We're talking about this axis and this axis, right? So two axes passing through the plane of the board. And one is going to be perpendicular to it. If I consider, a routine Cartesian system, right? And one axis perpendicular to it, right? What axis I'm talking about? I'm talking about the axis of rotation, right? Which for our purpose, right? We can consider them to be principal axes only, okay, right? So these are principal axes, and I allow them to pass through the center of mass, okay, right? And they are aligned with the con, that is the center of mass. For benzene, this is going to be, like the centroid of this hexagon right here, right? So now, it's very easy to see. By the way, before I get to this point, just one clarification. Even while discussing the spherically symmetric molecule, right, we only consider the principal axes, okay, right? So that's why, we are not considering the other components of the moment of inertia tensor. I just want to clarify that, okay? So please understand that once I align my principal axis along the center of mass, right, the moment of inertia tensor can be diagonalized to only have like three components, okay, right? So therefore the rest of the other components vanish. So that's why I only talk about 3 components of the moment of inertia. All right. So likewise, I'll not discuss the other ones, the Ix, Iyy, Izz, blah, blah. Is that clear? Okay. Now, similarly, here also, I only talk about principal axes and they're aligned with the center of mass. Okay. So the maximum number of moment of inertia terms that I can get are only 3. Okay. Please be clear about this aspect. Okay. So for benzene, right, we understand that 2 of the principal axes of rotation, I mean, of course, I'm talking about axes of rotation. Okay. Right. I've written off the rotation. I'll write it even better. Principal axes of rotation. Okay. All right. So principal axes of rotation are aligned along the center of mass. So I need to be worrying about 3 different components of the moment of inertia. Let me say that by convention, okay, right? Let's say IC, right, is going to be the moment of inertia I having maximal value. Okay, and then like IB, the next highest, and IA, right, the least. Are we clear, right? I mean, see, instead of like using the phrases Ix, Iy, and Iz, I'm just defining a convention wherein instead of X, Y, Z, I'm going to use C, B, and A, where C is the one corresponding to the maximal value of the moment of inertia, and IA and IB corresponding to the lesser ones. So in decreasing order. So always, whenever you read any book on spectroscopy or a book on spectroscopy for astrochemistry, right, you should always be seeing these notations IC, IB, and IA. But just recall the convention that IC is greater than or equal to IB, which is always greater than or equal to IA. Okay, so C is the larger one, and A is the least one. Okay, now having said this convention to you, it is easy to see that what's the formula for your moment of inertia? Your I is going to be given by sigma over I mi Ra square, where mi is the mass of the ith atom, right? And what is Ra? Ra is nothing but the distance, right? The distance of the atom, right, to the principal axis, right, passing through the center of mass. All right. So therefore, based on the symmetry of this molecule, it's very intuitive. It's very intuitive to tell you that for your IB and IA, right? In other words, the 2 axes which are in the plane of benzene, right? The distances are the same. Whereas, the distance of the axis which is perpendicular, right, that is going to be much higher. For example, if you consider this atom, right, this distance, right, for the in-plane distances, right, for the in-plane moment of inertia values are going to be lesser than the distance for the out-of-plane axis, right? So therefore, for molecules such as benzene, we have IB equal to IA, right? And both of which are less than IC. Why is that? That is because the distance of the atom, right, from the axis which is from one of the axes, right, is greater than the distance from the other 2 axes. Okay, so these are going to be the in-plane axes, and this is the perpendicular axis. So why are these, why did I call them symmetric? Well, there is some symmetric, but they're not completely spherically or cubically symmetric, as we saw with methane, etc. Okay, so in these cases, instead of like dealing with 3 different moments of inertia values, right, we'll be having 2 moments of inertia values. Okay, right, such that two of them are the same, and in the case of benzene, it so happens that they are going to be on the axis in the plane of benzene itself, right, and the other one is going to be the one perpendicular to it. Okay, so now for such symmetric molecules, I think they're also called prolate or oblate. I'll confirm what they're exactly called. They're called as oblate. So such systems for which IB is equal to IA and is less than IC, they are called as molecules having oblate symmetry. Okay, right? So they have like oblate symmetry, and for these, IB is equal to A and less than IC. But the point is, because I have effectively two moment of inertia values, I'll use this part of the board. As we discussed in an earlier lecture, so the point being that two I values implies we need two quantum numbers, two rotational quantum numbers to describe the rotational motion. So within the rigid rotor model, for rigid rotor, I'm writing RR. Your energy, okay, right? Your energy for such systems is given as Bj times J plus 1 minus A minus B times K square, where my B, okay, right? B is the rotational constant, and of course this is in centimeter inverse. Always important, right? You know, I can use whatever units for energy I want, right? We call. So I'm expressing it in terms of centimeter inverse. So my B is in terms of is the rotational constant along, okay, right? Along the unique axis. The unique axis is the one, you know, which has like the one value which is not equal. Okay, so rotational constant along IC. I'll just put it as IC, which is the unique axis, right? In this particular case, that's going to be the one perpendicular to the plane of the molecule. Okay, and your K is another rotational constant, right? Along IB and IA. I'm sorry, I've written it way in the bottom part of the board. So I just have an expression here, and E is Bj times J plus 1 minus A minus B times K square, where my B is a rotational constant along IC, and K, these are just ditto symbols, right? Rotational constant along IB and IA, right? So I have like two quantum numbers now. So I therefore have like two rotational constants, okay, right? Are we all good? Oh, I'm sorry, this is not K, this should be A. Sorry, so Bj times J plus 1 minus A minus B times K square. So where B is a rotational constant along IC and A is a rotational constant along IB and IA, right? Because recall, we no longer will be having only one prefactor, right? Because we have to describe the motion along the other direction also. So this is A and not K. I stand corrected, I clarify. I gave you an expression, right? I of course did not derive it. We did not even derive this part, okay? We just took it from quantum chemistry, okay? It is an easy extension to show that for molecules containing this symmetry, you know, where there are like two different values of moment of inertia, right? Such that one of them, I'll come back to this part a bit later, the connection between IB, IA and IC, okay? But then effectively there are just two different values of moment of inertia, IC and IB equals IA, okay, right? So for such systems, my B is a rotational constant along, you know, like the axis, which is unique, and my A is a rotational constant along IB and IA. It's not just the rotational constants, which are two in these cases, but also what? The quantum numbers. I will write it down here. So similarly, right, just like I have two rotational constants, I also have two quantum numbers, two rotational quantum numbers. J and K. All right. Now my J is, as you all know, going to be varying from 0 to all the way. I mean, all possible integer values are possible, and my K is always bound by J. Why is it so? I did not tell you, but it follows the derivation. Okay, right? Did not tell you why. I just ask you to take it for granted, but it can be mathematically derived. But because we are entirely, skipping the math in this course for the derivation, right? So this we need not worry about how this comes about, right? So this therefore is the expression, and the key idea to note is that the moment I have like two different moments of inertia values, right? I understand that two quantum numbers are necessary, and likewise, two different rotational constants are also necessary. All right, are we all good? Okay. Now, see, we were discussing about like molecules which have like two different values of moment of inertia. Okay. Now, there are cases such as, for example, in benzene, wherein my IB equals IA, right, and that is less than IC. Okay. But what is also possible? What is also possible is that, see, symmetric tops. Well, the word top is just a synonym used for molecule in our case. Okay, right? Another possibility is my IA less than IB is equal to IC, right? In other words, in the case of benzene, as we saw, right, we had the unique value as corresponding to the greatest value of moment of inertia. It's also possible that the unique value could also be corresponding to the least value of moment of inertia, right? So we were discussing the case of IA less than IB equal to IC. This was the other instance wherein the moments of inertia, we had like two distinct sets of moment of inertia about the principal axis, and such that the greater values were equal, and then the least value of the moment of inertia was individually on its own. What is an example of such a molecule? Take the example of methyl chloride, CH3Cl. So this is methyl chloride, CH3Cl, and as you can see, this molecule is a tetrahedral. Its molecular shape is tetrahedral. You have in fact been studying about this right from probably your 11th or 12th standard, and also in fundamental organic chemistry. Now, if you notice this, these three hydrogens, they lie in one plane. So you can imagine this being a pyramid with the three hydrogens forming the base and the chlorine situated at the apex. So I'll just write it down. Three hydrogens, they form, they are in one plane, and they form the base of this tetrahedron. And if you notice that along the axis, let's say you consider the axis which passes through the CCl bond, this particular axis. I'm talking about the vertical axis along the board. Now, if you were to rotate about this axis, you notice that majorly, the three hydrogens, the motion involves the rotation of the three hydrogens, right? So consider vertical axis. When I say vertical axis, I'm talking about this specific axis along the CCl bond. Now, if we rotate about this specific axis, right, we note that the rotational motion involves the three hydrogens which are much lesser in mass with respect to the Cl, right? And also note that for this specific molecule, the center of mass is going to be lying closer to the Cl than to the carbon, right? Than to the hydrogen, sorry. So it is going to be lying somewhere here. Okay. So considering all of this, you notice therefore that this specific rotational axis is going to lead to the least amount of moment of inertia. So therefore, this vertical axis is going to be the A axis, and the moment of inertia along this axis is what is going to be IA. So this is IA, and it's easy to see that this specific rotation along this axis is going to be the least value, is going to correspond to the least value. Why is that? Because with respect to the Cl, the mass of hydrogen is much lesser, so therefore rotation about this is much easier. That is one point. Now, if you were to consider the two other perpendicular axes, let's say, we're talking about this axis versus this axis, and also, the perpendicular one, right? The one that is passing through the board. Now, if you rotate this molecule about the axis, axis passing along the board like this, you see that the chlorine's motion is involved, right? The chlorine's rotational motion is involved. Likewise, if you also, were to rotate it about this axis, right, then also the chlorine's motion is involved. And you notice that by the symmetry in the system, there is a priori, in the absence of any external field, a priori there is no reason to believe that the motion along the rotational motion about this axis, that is the horizontal axis along the board, and another axis which is perpendicular to the board, that both of them are going to be any different. So therefore, they are going to be the B and C axis, and you already see that rotation about these two axes are kind of equivalent. They are in fact equivalent in the absence of any external field. So therefore, your IB is equal to IC. So we've established that IB equals IC and IA is less than both IB and IC. So this is a specific example of a molecule which has the opposite order of moments of inertia with respect to benzene. I think benzene was called as oblate. So this molecule, methyl chloride, is what is called as a prolate symmetric top. Okay, so this is just one more example. This is one more example to highlight the difference between benzene, which was an oblate top, wherein the magnitude of wherein it was IA equals IB, which were both less than IC. But here, IB equals IC and IA is less than both of them. Okay, so these are the two types of symmetric tops. Kindly note. So on that note, I think I will just end this lecture. This is lecture number 61. If you are looking at this tutorial, looking at this video, you may notice that there is a slight discontinuity in the sequence. That is because I had earlier made a mistake about the molecule, and that is now being corrected in this edit. So that could lead to some discontinuity error, but don't be confused. I will also ensure that the continuity of the video is being made very clear to you all. I think on that note, I'll end this lecture and see you all in lecture number 62. Thank you. Have a good day.